So water quality modeling. Our objective is to actually identify and simulate the movement, transformation, and changes of water quality parameters. And we're going to be doing this along the coattails of an extended period simulation to help us approximate whatever the results are going to be and project those results in the hydraulic model. This is an example, an actual thematic results representation of chlorine concentrations or chlorine residuals in a system, predicted values anyway, because quite honestly, we're not going to be sampling chlorine at hundreds of nodes in a system. It's just we don't have the time, we don't have the money, the manpower to do it. Maybe someday down the road we might have a lot more sampling sensors. However, what the hydraulic model does in combination with the water quality model, it allows us to fill in the gaps from, say, 3 data points. It allows us to calibrate our model, make sure it's running properly, make sure our decay rate is running properly, to ultimately predict what the chlorine concentrations and residuals should be in parts of the system where we don't have sampling points and give us confidence. And regulatory agencies recognize the use of these, provided that the models are calibrated. There's some justification to demonstrate that it's a well-calibrated model to draw the conclusions without, and also what I've seen in the past is that means the systems can actually reduce their amount of sampling volume and maybe have some real dollar savings in the long term by having a water quality model running. So remember, what this is trying to do is actually mimic the transformation and movement and mixing of the constituent, whatever it is, throughout the system. And in a little bit in the next few slides, we're going to get into constituent types and how those constituents behave in the system and how we get to that information. But this is kind of at the high level what we're trying to achieve with water quality modeling. Now, why do we want to do it? Well, there's a compliance requirement. Maybe it's to reduce the compliance requirement, the volume of sampling or something. And another thing, too, is that water movement isn't linear. It's going to change over time. It's going to change over operations of our system. So we want to be able to see if different operation control settings are going to impact water quality. And then the reality of it, too, is that systems may have more than one source. So as those sources vary across the system, and maybe at certain times a well field is used versus a groundwater reservoir is used, and those two different water sources may have a higher total dissolved solids, one may than the other. So is there a maximum point at which the mixing is occurring in the system that the TDS is too high? So we can use a water quality model to help dial in what that range should or shouldn't be of blending. And again, this is to help reduce the number of sampling points and give us a more broad picture, and to test out why something might be happening, why we might have water quality issues somewhere. As I was mentioning, giving an example earlier in one of the other presentations, an organization was having water quality parameters at a pump station, and it turned out it was because of the pump controls that a pump station was not able to operate as well and as often as frequently and push out as much volume as they thought. Therefore, it was causing some water quality issues and the water quality to deteriorate in the tank. So water quality actually means different things to different people. So let's kind of take a broad brush across all of it here. It could mean whether or not tanks are covered, if there's cross connections in the system. It could mean that there's lead and copper in pipes. Could actually mean disinfection, decay, and DBP. DBP is disinfection byproducts. These are harmful things. And things that we're going to model. So those two we're going to really kind of focus on, or at least the disinfection decay. Flushing, it could mean that. Water quality modeling could be security and prevention, or modeling if a nefarious act occurred in the system, how to isolate it and how to flush it out of the system. It could be, water quality could mean you're investigating taste and odor complaints. It could be tanks and mains, contaminated sources, litigation. 1977, I believe, there's, EPA, Clean Water Act. There was a lot of litigation that happened around that time period in the U.S. There was a lot of, a handful of organizations that were brought to court because of contamination, and there were deaths, and so a lot more attention was placed on water quality. And I don't think it was 1977. It was I'm blanking on the exact time period. But a lot of litigation, and you could also use WaterCAD and WaterGEMS and the water quality model to help justify what happened, when it happened, where it came from. Now, there's a great deal of questions that can be answered through a really effective extended period simulation model. You can check the impacts of adding a new tank, where to add a disinfection booster station, where you need to add or boost a chlorine or chloramines, whatever disinfectant you're using there. Maybe you are trying to decide if you want to connect up two systems that have two different constituent values, like total dissolved solids. Is that going to have a disfavorable impact? You're extending the distribution system, therefore maybe you're putting in another transmission line that's going to go out further. That's going to increase the water age and using that as a surrogate to water quality. It may have poor water quality results. New services, sizing of pipes, whether you need to do pipe cleaning and lining to increase the C factor. So it could mean quite a few different things here from the design perspective. It could help you, again, decide your disinfectant levels, how much chlorine you should be dosing to get the optimal residual out in the system, out in tanks. But as we get into the water quality modeling in a bit more detail, it's not just that doesn't mean it's just going to be very easy, it's going to spit out the number. You as the hydraulic modeler are going to have to do some legwork and calibrate the model to make sure that what the model's predicting is actually realistic. So we're going to get into a lot more detail on that here in this talk, but this is just the fundamental, again, scratching the surface of water quality modeling. You can create different disinfectant constituents to model, let's say chloramine or chlorine. Balancing water sources with total dissolved solids. Maybe you're adjusting PRVs and changing how pressure zones are operating to ensure adequate operation and movement of flow. So there can be quite a few different operation standpoint things that you can answer with the model. Some other uses of the water quality modeling: determine historical exposures, litigation, as I mentioned earlier, trying to recreate a cross-connection event. Something happened and you wanted to see the impact or the reach of that event. Creating complaints, and I've got a good anecdotal story that I'll share with you here in another slide or so about recreating complaints and trying to overlay an event with user complaints to see if there was a correlation hydraulically that you could prove or disprove. Water security, so a lot of things. Here it is. Here's some of the dates that I was looking for. 60s and 1960s and 70s, pollution awareness became a big deal, and by the 1990s, we were modeling water quality in tanks, and that's also about the time that you start seeing vendors starting to sell tank mixing devices. And as we're going to touch on in the workshop here a little bit further along, that with those mixing devices that are put on tanks, while they were sold very frequently, sometimes what you'll end up with is a tank that's locked out hydraulically from the system, that the mixer hasn't really helped and alleviate that issue, but what it's done is provided you really well mixed old water. So we'll touch on that too, about tank mixing and with water quality modeling. Let's think about what actually occurs in a hydraulic model or in the water system with respect to water quality. There's the source, and there's some value that the constituent has at the source. Maybe it's 0, or maybe it's something that comes from the treatment plant. There's some value of chlorine that's put in there. From the well field, there's some total dissolved solid that comes from there, maybe. So there's a source. Then there becomes the operation of the system. That's how the pumps go on and off, and how the control of how frequently the tanks are drawn down to 30% or 20% or something. And then there's the transport and transformations, the actual reactions that are going on, if any. Could be just mixing, related to mixing, or it could be due to transformation from some reaction with another constituent. And then storage, too, because the tanks, they're quite a bit bigger in diameter than, by their own nature, they're quite a bit bigger in diameter than a pipe. So there's going to be some more residence time for those tanks. And then there's significant variations in the water quality model, perhaps over time and over the region of the hydraulic model itself. Just want to try and differentiate the two here for you. The hydraulic model is really the first piece of the puzzle of a water quality model, and it's imperative that the that you take the model as it's an approach to water quality modeling, but you have to get to a good viable hydraulic model first, a well-calibrated extended period simulation model, or you risk deviating from the real-world predictions quite a bit. And this is the workflow for water quality model. Basically, you start off with the data entry, and we've been talking over the past in the fundamentals course, and then during this past few days, we've been talking about data entry and how to get it into the model. Once you have your initial hydraulic conditions set up, you solve that model, so you would compute it as an extended period simulation, and then that's going to generate, for every time step, it's going to generate data. Once the controls reach the end of the time step, great, you've got all of these snapshots in time, and then the initial water quality conditions are entered. You as the modeler, you're entering this all at once and pressing compute, but this is really kind of what's happening behind the scenes. Once it runs the EPS, then it applies the water quality conditions, then it solves the water quality model for the equations that you provided it, goes through all of those time steps, and then you get results. So really this is all happening kind of all in one pass, but I just want to let you know kind of what's going on under the hood. Water quality is really, remember, a combination of the hydraulics in the system, the transportation in the system, meaning how the water got to where it needed to go, the bulk reactions. This is the reaction in the body of the water of the pipe and the body of the water in the tank itself. And then a little bit more uniquely, the reaction of the water quality parameters along the wall of the pipe, because there's some things that can happen there because the velocity is lower, the surface area is higher, there could be biofilm, there's things that come up. And then, of course, how the tanks themselves mix. If this is kind of your first introduction to water quality, you could kind of think of these as individual topics that you might want to take a deeper dive into. Hydraulics, obviously, you spend a lot more time on so far in this class, but transport, bulk reaction, wall reaction, tank hydrodynamics, these are some other pretty big areas for water quality modeling that are worth learning a bit more about. So what you're going to need to feed the hydraulic model is the source concentrations, whatever it is, the values coming from the treatment plant, from wherever else, treatment plant and well field or something. Initial concentrations in the tanks, the reaction rates, how quickly the chlorine is decaying, how fast the disinfection byproducts are being produced, and what does the tank mixing model really look like. You'll have that choice. Any chemical feed rates where you're adding something. So there's some input that you as the hydraulic modeler are going to put in. You have the water coming in from the, let's assume it's a treatment plant, and you're trying to get to the tap. You have cross connections throughout the system where you've got some water that's a little bit older than the new water and it's mixing. You've got water coming in from reservoirs, from tanks. That's been in those tanks for quite a bit. So water's going into the tank, old water is, and new water's coming out, or maybe it's a different kind of tank where, water goes in and water comes out in the same pipe, the same location in the tank. Then you also have transformations in the water itself moving through the system, transformations in the tank, and then there's transformations along the wall of the pipe. And while it may seem like that's not too big of a deal, it's actually a calibration parameter in water quality, but albeit a more difficult one to get to. And then you have things like leaks and things that are pretty hard to account for, but you could have leaks in the system where flow is leaving somewhere. You can model that. So within the confines of WaterGEMS and WaterCAD, the different types of water quality modeling that you'll be able to do is source tracing, where you would trace where a constituent came from. Water age, which you're pretty much looking at how old the water is in the system. Constituent growth, which is something's growing, something's increasing. And constituent decay, meaning something's decreasing. So water age itself, it's going to be calculating the age of the water over each node, but also it's taking into account the residence times in the tanks and the reservoirs. So you'll be able to set whatever the water age is in the reservoir and the tank, and that does not necessarily mean that the tank water age is 0, because if you took a snapshot in time in the water system you're working on right now, the water's been sitting in the tank for a particular number of days or weeks or something. It's been there. It's not 0. It's something more than 0, because it didn't just get filled at this very moment, meaning completely. There's some percentage of older water in there. So you have to make those assumptions and base them off of something that's somewhat plausible. Water age is pretty high at dead ends, and tank initial condition is really important here. So now let's start digging into the different types of constituents. The conservative substances that you might model, these are ones that are changing only due to mixing. So conservative substance changes due to mixing. Non-conservative substances are changing because of some other thing that's going on, and that thing could be chemical, biological reactions, physical processes, something else that's going on. So conservative, mixing, non-conservative, some reaction. So the typical constituents we'd be looking at, DBPs, fluoride, chlorine, chloramine, TDS, total dissolved solids, those are kind of things we'd be looking at. So now let's actually see how we can apply these more precisely with WaterCAD and WaterGEMS. But first we have to understand what type of behavior these constituents follow. Now, the slide here, what we're not going to be doing in WaterCAD and WaterGEMS is we're not putting in the chemical makeup of the water. We're not putting in all of the elements that are going into the system and the hardness and the pH and the temperature and all of the other variables that come into play. We're not putting that all in. What we are doing is we're putting in a decay rate. The constituents are going to decay proportionally to concentration. They're going to decay at some rate. So using CO, C sub O, as the initial concentration, we can derive an exponential decay rate, where K is the coefficient that we're going to change, T is time. And in this case, chlorine would follow the pattern of a first-order decay, to where it continually and exponentially begins to decay over time to where at some point that it will approach zero. A zero-order growth, on the other hand, or decay, let's say in this case zero-order growth, an example of that would be something that grows proportional to time. And the only real thing that grows proportional to time is water age, so that would be zero-order growth. So age is a great example, zero-order growth. And then on the other end, first-order growth, instead of zero-order growth, not linear, something that exponentially grows over time. What's potentially growing over time, and then why does it reach some concentration max? DBPs, disinfection byproducts, also called harmful disinfection byproducts. That would be haloacetic acids, HAAs, and trihalomethanes, THMs, some things that we don't like to have forming the system because they're carcinogens. Now, why do these reach a point where they're no longer being formed? Why would they reach a Cmax, where that exponential growth tends to level off? Source material runs out. So it runs out at some point. Cmax cannot exceed Cmax because it's no longer there, but it's still going to grow, have a growth rate that in this case is minus KT. So now let's think about this in a real world situation. You've got some network, you know the flows in the pipes, you know the velocities and the pressures, and you know the reaction rates, meaning you know how quickly chlorine decays in the water. And I'm going to talk to you about how to get to that in a moment. But let's say for now, argument's sake, we know that. We know what the source concentrations are, what we're getting from the water treatment plant. We know what the initial conditions are in the tanks. Check mark. We know all of these things. So then our objective is to determine the concentration at all nodes at all time periods or time steps. How this is accomplished, currently we model these nodes as completely mixed, where the node, in this case C1, it's coming from C1, pipe 1 over here, has a certain flow rate and concentration, and pipe 2 has a certain flow rate and certain concentration. We assume that these are completely mixed at the node, leaving the same concentration, leaving both pipes out of that node. Now, however, is that really the case? Can one source flow slower maybe than the other and cause the node to partially be mixed? Does it matter, kind of how that works really? So the answer here is yes, that could kind of be happening, that the node may not be completely mixed depending on temperature or depending on the hydrodynamics in that junction. But then when you zoom out a little bit further from the system, especially in loop systems, you zoom out a little bit further, it tends to really not matter as much anymore. There was a paper done 2007, I think, by Sandia. There was a paper that was done on mixing, incomplete mixing in junctions, and yes, it's real. It's reality that may be happening that due to temperatures and concentrations, there may be some lack of mixing that happens. But again, when you zoom out, this issue at one junction tends to matter a whole lot less. Chlorine reactions at the pipe, within the pipe itself, there's actually two different types of reactions that are occurring. There's the reaction in the bulk of the body of the pipe itself, of the water there, and then there's the reaction at the boundary layer. And this is due to the slower velocity along the edges of the pipe. Happens just the same as a river. The water's slower along the edges. And there's more surface area along the wall of the pipe to where there can be more bacteria, more film, or something that's causing greater decay. So we can, in the model, we can adjust that boundary reaction rate different from the bulk reaction rate. What the reaction rates really are, they're a log of, in this case, chlorine, decay over time, reaching zero at some point. What you're going to end up needing to do is to kind of come up with your own reaction rate for your system. There's book values that you can start with, certainly, but this is a little bit complicated to get to sometimes if there's a lot of other mixing in your system. How you get to the bulk reaction rate itself? Well, first, you're actually going to have to test that somewhere, and I believe I've got a slide in just a little bit that'll show you how to do that. But generally, it's a first-order decay for chlorine. In the case of chlorine, there's some decay rate, and the decay coefficients are going to be somewhere between 0.05 to 15. For most of the decay rates in the model, you'll start with 1 if you just don't have anything, and you'll just run with the digit 1 for a decay rate, but then you're going to need to come back and calibrate that value. So what the chlorine water model is doing is actually predicting the chlorine residual throughout the system, and in this case we have graphed the chlorine residual throughout, looks like a 28-hour period for one particular tank, and we can see how that chlorine level in that tank changes over time. Maybe this is changing due to mixing, maybe it's changing due to how quickly that tank is turning over. But we can see that it's ranging somewhere between about 0.2 and 0.23. So it seems to have kind of leveled off at that kind of range. So we know that's what the expected range based on the model. That's what we'd expect to see in that tank. Now, how do you get the decay rate that you're seeing as an effect out in the system? Well, a first guided step would be to collect 8 to 12 sterile bottles of water. So make sure the bottles are clean and sterile. Collect 8 to 12 bottles. Make sure you fill them up to where there's no air bubbles in the top of the bottle and it's just water. That way there can be no gasification occurring. Put them in a constant water temperature place, a water bath or something, to keep them fixed to where they're going to be maintaining a particular temperature all the way through. And then at various intervals throughout the time period. Now, if you have a lab, this works out real easy to do. Every couple of hours, you would pull out a bottle and measure the chlorine residual. You continue to do this till you've reached, the typical age of your system, water age in your system, and you're still measuring the chlorine. So you're in effect kind of in a laboratory condition, measuring for your water quality parameters and all of the variables that are in there, what the actual chlorine decay rate is. And remember, this is the bulk reaction rate, not the reaction rate that's happening along the pipe, but this is just kind of the body of the water, the body of the pipe itself. So you then plot those reaction rates, or not reaction rates, but the actual chlorine value. And from that line that you get, you're able to digest what the actual K value is based on the declining concentration over time. So use the equation, natural log, figure out what the K value is. Then that K value is actually what you're going to feed into WaterCAD and WaterGEMS. So you're not putting in, chlorine and magnesium and pH and temperature and everything else. You're putting in the actual reaction rate that you derived in the lab. Okay, so wall decay, that's a little bit of a different story. Maybe it's due in part due to biofilm, C factor on the pipe, but there's some decay rate that's different from the bulk reaction. Wall reaction rate, again, it's different than bulk reaction rate, and this is more or less determined experimentally, where you're going to adjust the model to see if you can get the values that you're getting in the real world. The ranges are going to go from 0 to 1. 1 is a pretty hefty wall reaction rate. 0 would be no wall reaction rate. And how this is expressed, the K sub wall, it's expressed as alpha divided by the Hazen-Williams Z factor. And so you can look at that and say, oh, great, I'm going to be able to solve the K just by knowing what the C factor is. However, alpha can then range anywhere from 0 to 100. So you're still going to need to come up with kind of a guess value on what it should be. But I'll show you on the next slides here kind of how you can start changing that parameter in the model and then watching the observed data points and how the model begins to overlay those data points. Calibrate your equipment. Anything that you're using in the lab, make sure you calibrate it, follow lab procedures, because whatever values you're getting out of the laboratory results here, you're going to apply to the whole model. So it's going to have a direct effect on your results. And so the quality, or whether or not you need to repeat the test to improve the confidence of the values that you get, you might need to do that as well. So this is an example for the wall reaction rate. The different colors here on the lines represent different wall reaction rates. The green dots, these are actually the observed data points. So we've already done our bottle test, we've already calibrated our model, and now we're looking at the predicted values in the system for chlorine concentration. And the first wall reaction rate of 0 doesn't work. As an example here, we try another wall reaction rate, we try another wall reaction rate. Now we start finding out that maybe we kind of know what that wall reaction rate is now, because it looks like it's the red dotted line. So then that's how we would start experimentally deriving what the true wall reaction rate should be, and then use that for the model from that point on. And you can choose to model it without the wall reaction rate, but you have to accept that your reaction rate is then being dampened somehow, or being impacted by the additional reaction rate that is a known value, a known impactor out in your system. So you're going to have some deviation there. Okay, so use the extended period simulation, a well-calibrated extended period simulation. I need to do that. Tracer test studies. These will help you find closed valves, and to run an extended period simulation tracer test study, you need to have something that you can add to the water system that is only going to change due to mixing. It's going to allow us to see the flow path of water, because we'll see fronts of that concentration hitting our sampling point, and then go compare that with the model and see if that's really what's happening. Because there's no reaction rate going on, it's just changing due to mixing. This really does help us see how our model's behaving and get some more insight. So how this works is you inject the tracer at some source, and then you measure that concentration of that tracer at various places. You may not have this many measurement points, but you would be measuring it in different places at different intervals. Maybe you're moving along the line, following that front and measuring it at different times. You collect the operational data to make sure that you have the pump and tank and valve operation and everything going on at that time, the controls and everything. And then you come back, sit in front of your computer, run the hydraulic model, put in that concentration that was added, and also with the user data extensions that I was showing you earlier, put in the user data extensions, and that will be the field that you'll see mapping the data in the graph for you. And then you're going to look at how well the predicted values match the actual observed data. Tanks are different than nodes. They actually have storage. There's going to be a water quality change there. Tanks handle mixing. We've got different types of tank mixing models. I'm going to try and show you a little bit about tank mixing. Tanks have long residence time. You would have decay rates of your chlorine. You might have bacterial growth, but that's a bit more complicated, because hot water might grow bacteria faster than cold water, and that's going to be a really, really tough one to make sure you have the right curve to model temperature changes throughout the day. And poor mixing, that can cause more water quality issues to develop, so we can have and model a poorly mixed tank in the hydraulic model to see if that will help us calibrate better. As far as calibration goes for tanks, one of the most important variables is what is your initial condition. The initial condition for, say, a junction, water moves through a junction pretty quickly, water age, then there's changeover. That happens really fast in a junction. However, in a tank, it's going to take some time. It's going to take some long time. This blue line right here, kind of at the bottom, the initial concentration was set at 0, and it's going to take days and days and days for the model to catch up with what the real water ages in the tank to where you start seeing the model repeating over time and cycling. So starting out with the correct initial condition of some well-calibrated tank model, in this case the green line, you would see the tank start to oscillate and see kind of a pattern develop and emerge. So that's probably a more realistic initial condition or initial concentration for the tank. Okay, so with tanks, we need to be careful about water age and disinfectant loss. We need to have good mixing. We don't want the tanks to be stagnant. So to alleviate this, we might increase the velocity input of the tank. We might add a mixer, or we might ensure that the tank drawdown happens frequently. This is an example of inlet mixing. There's an inlet in the middle of the tank. Maybe it's a neck down reducer that causes additional flow velocities and cause turnover in the tank. Maybe there's some different types of inlet and outlet valves on the pipe. There's duckbill and different proprietary versions that allow water to go one direction and ensure that there's turnover in a tank. Or there's the physical mixers that could promote the same kind of behavior. But keep in mind, a really well mixed tank may just be really well mixed old water if it's hydraulically locked out or something. You could also, with the tank, have mixing conditions that are temperature relative. So dense water is cold, and if you have a hot tank and groundwater comes into that warm, hot tank, the cold water is going to stay at the bottom. And if you have an inlet outlet at the bottom of the tank, then the first water that came in is the first water to leave, leaving the warm water to stay in the tank longer. Vice versa, if you have the water's cold in the tank and you have warm groundwater come in, that warm water is going to rise to the top and it's going to be more buoyant, and you're going to have kind of plug flow in the tank where the oldest water is leaving first. That might be good, but you can simulate these scenarios with the actual tank mixing model. So keep in mind, lots of different ways that water can enter tanks and leave tanks. Maybe it's a clear well, like the box version here. It's moving as flow through the system. Maybe you've got really large diameter tanks where right at the middle of that diameter tank, it mixes really well because water's coming in and out. But at the far reaches, the outer perimeter of that large diameter tank doesn't mix so well. So we can handle kind of multi-mixing combinations in tanks. We do this by having a tank that can be set as complete mix, to where it's like there's a mixer and it's completely mixed. Plug flow, as the oldest water leaves first. Last in, first out is another option. So the very first water that came in, that's the first one out. And then two compartment one here. This is one where you can set the percentage of the tank that's completely mixed in dark green versus the other portion of the tank, maybe it's 80%, 50%, 70%, that is plug flow. That's not very well mixed. So that's kind of a customized variant on the tank. And just to show you how this can impact tank modeling and mixing, this case example is looking at chlorine concentration in a tank and changing around the 4 different mixing models that are available for the tank. So using only the tank mixing model variations in 4 different scenarios, you graph that data for the predicted chlorine values, and you can see the blue one and the green one have quite a bit of variation. The 2 compartment, however, maybe that's more realistic. Maybe you're doing some sampling at the tank to see if that's really accurate or not. Whereas the completely mixed one, the red one, you can see that's got the most narrow band as far as performance of the tank, because it's assuming that as water comes in, it's completely mixed in concentration with the rest of the tank, and whenever it leaves, that's a completely mixed concentration leaving. It does tend to matter, the tank mixing model, so I would encourage you to really understand the tanks that you have, how the flow moves in and out of those tanks hydraulically, if you have any devices there, no devices, where the inlet is, where the outlet is. Also, what is your confidence that it's very well mixed? To run water quality model, you will need to have an extended period simulation that's calibrated, set up the constituent reaction rates, whatever those are, for the constituent you're interested in. Select the constituent in the alternative, so chlorine or total dissolved solids or something. Set up the representative scenario, maximum day, minimum day. Maybe you care about minimum day because the tanks are going to sit longer. Maybe that's of importance. So that's the one you pick. Adjust the calculation options to basically tell the model, hey, I want you to run a constituent analysis or a water age analysis, and then press compute. To set up a tracer, you would create the constituent that you want to trace, pick a particular scenario, and then enter in the trace source elements where you're going to be measuring the concentrations at. So a little bit different there. You can trace multiple sources at once and see where multiple sources are coming from and when they mix and where they mix. So that you can do without actually, you're not really putting in a constituent, you're just seeing how well they mix and where they mix hydraulically. This is purely a hydraulic standpoint. And maybe this is before and after operational controls that we've changed and operational highs and low elevations for tanks. And we can now see, based on color coding, we have a lot more mixing in the model simply because we changed up controls in the system. So maybe this is kind of where you're heading. And we can graph the sources of the water at a node. So in this case, we can overlay trace and flow and cumulative volume all on one chart with one scenario. Create some pie charts. We can really get really creative in how we demonstrate the model. And don't forget that we can also play the model over time and record the changes in values. Okay, one of the last few slides here to get you kind of thinking about using WaterGEMS and WaterCAD water quality model for security. Maybe there's a physical disruption, a power shutdown that you're trying to model. What's the impact? This could be realistic where you have power failure at a pump station, but it could be a human act that took that pump station out. What's the impact if that's out? If there was any biological contamination, how long would it take to get completely into the system? Could it be isolated by control valves? Would you actually recognize that only one part of the system is going to be seeing that contaminant? Or if it was chemical, or maybe there's just a loss of customer confidence somewhere because pressures are low and you're trying to understand that, why it is. pH, temperature, solids, entering in actual chemical reactions and how those reaction rates occur actually in the hydraulic model. That's something we're likely to see in the future. For now, we're really looking at building the confidence of the water quality models with you supplementing the reaction rates for now. So computers are going to be a lot faster in a couple years and be able to handle eight processor computations with chemical equations in there. It's just right now that's a little more complex than computer systems can handle, especially when you throw in pH, temperature, and time and everything else.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.